All right, so in Schoology, once again, you will see a set of notes for pH of salt solutions. So you can go ahead and you can use those notes as you need to. Great. All right, so ions can be either acidic or basic. For example, we have in previous lessons calculated a Ka for the ion NH4 or the Kb for the ion F minus. So if that's the case, we know that those ions can be acidic. So how do we know that NH4 is an acid? How do we know that F minus is a base? Well, they're going to react with water to create either H plus ions or OH ions by splitting that water up through hydrolysis. Thus, a salt, like NH4, can be either acidic or basic, depending upon how the ions that it's made up of react with water. All right, so we're going to go ahead and break this down depending upon the kind of ion that we have. Okay, so let's start talking about anions in water. All right, so the very first thing we're always going to be looking at for all of these ions is what is its conjugate base. Okay, and so the first situation we're going to explore is what happens if the anion is a conjugate base of a strong acid. So for example, something like Cl minus or I minus or Br minus. Okay, if it's one of those and its conjugate is a strong acid, then we wouldn't have an equilibrium situation. So they're not going to react with water. There'll be no change in OH concentration, so no change in pH. Okay, so as an example, again, Cl minus, conjugate acid is HCl. So we know that if I put Cl with H2O, we will not have a reaction because the reverse reaction is that of a strong acid with OH in the water. And so as a result of that, this reaction will not proceed in the forward direction. Okay, and so as a result of that, addition of chloride ions to a solution does not affect the concentration of OH. And so as a result of that, you have no change in pH. But what if instead is the conjugate base of a weak acid? So that would be something like the methanoate ion, HCO, or F minus. Okay, things who are the conjugate base of a weak acid. If this is a situation, we have equilibrium possibility, and so they will react with water, and so the OH is going to increase and the pH increases. Okay, as our example, let's use the F minus ion. The conjugate acid is the weak HF, so you're going to end up with a situation where F minus will react with water to produce the HF acid as well as some OH minus ion. So when we add a salt in that has an F minus ion in it, we go ahead and this reaction is going to go ahead and shift to the right. That's going to increase the amount of OH. That then will change your POH, which will then, of course, change your pH. Okay, so having that anion in water will change the pH of the solution. Okay. Third situation with anions that we want to be aware of are amphiprotic anions. And remember that amphiprotic anions can either be acidic or basic. They can either add an H or get rid of an H, right? And so in order to figure out what's going to happen with an amphiprotic anion, what we need to do is we actually need to look up their Ka and their Kb, and we need to compare them. If the Ka is greater than the Kb, then the pH decreases because the acid dissociation is greater than the base dissociation. If Kb is greater than Ka, then the pH is going to increase because the base dissociation is stronger than the acid dissociation. So example of this would be the ion HSO3. Okay, it is the conjugate of a weak acid. It is also the conjugate of a base. Okay, so if we go ahead and look at the reactions that can involve HSO3 minus, one, it can react with H2O to form H2SO3 and OH minus. There's its base reaction. It can also lose a hydrogen ion to form SO3 2 minus and H plus. That's its acid reaction, Ka. All right, so if we take a look at these and we say, okay, what one is stronger, we can see that Ka is in the order of 10 to the negative 8th. Kb is 10 to the negative 13th. So this is a situation where Ka is greater than Kb. And so as a result of that, you're going to get the acid reaction happening, and the pH is going to decrease. Okay. Situation is very similar with cations. If the cation you have is the conjugate acid of a strong base, so that would be, for example, like Ca plus 2 or Li plus. Okay, we would not have an equilibrium situation, so they will not react with water. So there'll be no change in H plus, so no change in pH. Okay, so here if we look at Na plus, the conjugate base is NaOH, which is a strong base. So that means that the only reaction that can happen here is the reverse reaction. And so as a result of that, you end up with a situation where the addition of Na plus does not affect H plus. All right, but what about the case where your cation is the conjugate acid of a weak base? So this would be things like any other positive ion, for example, silver, okay, or zinc. Under this situation, just like with anions, an equilibrium situation does arise. It's going to cause the H plus to increase, so pH is going to decrease. Here's our example of this. We've got aluminum plus 3 ion. Its conjugate base is the weak base, AlOH3. So that means that Al3 plus will react with water to form that weak base, and in the process, it will be pulling off some hydrogen ions and leaving those behind. So the addition of this particular deal will shift the reaction to the right and increase the concentration of H plus, which means that our pH will go down. This is especially true or especially noticeable for small ions with a high charge, like iron or aluminum. You'll notice over here, we've got some 2+ ions above the line that also tend to be relatively larger ions. Below the line here, we have iron, chromium, aluminum, again, 3+, adding that extra charge on, as well as having those be smaller ions, etc. Goes ahead and changes and makes those Kas much, much bigger and makes the pH effect much more noticeable. So greater charge and smaller size makes a cation more acidic. All right, so now an ionic salt is going to have both a cation in it and an anion in it. So if you're trying to figure out, if I put, for example, sodium chloride, NaCl, into water, what is going to happen? What is going to happen to the pH of that particular solution? All right, so if you think about this, 4 scenarios arise. 1, if I put that salt into water, will the pH be neutral? Well, that happens when both the anion and the cation don't affect the pH. In other words, they are both the conjugates of strong acid and a strong base. All right. pH is basic would be if the anion does affect the pH, but the cation does not affect the pH. pH is acidic is if the anion doesn't affect the pH and the cation does affect the pH. Okay. Last but not least, let's say both the anion does affect the pH and the cation affects the pH. They both have conjugates that are weak. Well, in that particular case, that's where we go and we compare the Ka. Kb of the anion versus Ka of the cation. All right, so here's your example. I have a whole bunch of different ions or salts here. Your job is to determine whether these solutions are going to be acidic, basic, or neutral. Take them one at a time, and then we'll come back and we'll talk about them. Okay, so let's look at the first one. We've got a barium ion and an acetate ion over here. And so if we think about this, barium's conjugate would be BaOH2, which is a strong base, so there's going to be no effect there. The conjugate of CH3COOH is going to be a weak acid, So this will react with water to form acetic acid and OH minus, right? So in other words, this will produce OH minus ions. So this one here is going to be basic. All right, let's take a look at the next one. We've got NH4 plus. The conjugate base for that is going to be NH3. That is a weak base. And so this one will react with water, giving us H3O plus plus NH3. Okay, so as a result of that, we are getting H3O. We're getting acid being made, or acid ions being made. And so we know that this is going to make it more acidic. Chlorine, its conjugate acid is HCl, which is a strong acid. So that means it will have no effect. So overall, this one becomes an acid. All right. Next one we have on here, methyl ammonium bromide. All right. So we have the methyl ammonium ion here. Its conjugate is going to be methylamine, which is CH3NH2. That is a weak base. And so once again, we're going to have a situation where we will react with water to form H3O plus methylamine. Okay, so once again, H3O is being produced there, and so this is gonna cause the solution to be more acidic. Br is the conjugate base of HBr, which is a strong acid. So again, there'll be no effect there. So overall, this thing is gonna make it more acidic. Next one we have is KNO3. So we have K plus ion, we have NO3 minus ion. Conjugate acid of K, or base of K plus, is KOH, which is a strong base, so there'll be no effect there. NO3 minus conjugate acid is HNO3, and that is a strong acid, and so there'll be no effect there. So this is going to be neutral. Last but not least, we have aluminum perchlorate. So we've got aluminum ion, Al plus 3. We've got the perchlorate ion, ClO4 minus. Aluminum conjugate base is aluminum hydroxide. That is a weak base, so we will react with water here, giving me AlOH3, 3 waters, plus 3H plus. All right, so that means H plus is being produced, so this will make it acidic. HClO4 is the conjugate base of HClO4. So that's going to be, that is a strong acid, and so this will not affect the situation at all. And so overall, this one, again, is going to be acidic. Hooray! We did them right. All right, so that then brings us to pH calculations for salts. So if I put a salt into solution and it does affect the pH, how do I go ahead and do calculations having to do with this? Well, here's our example. A 2-liter solution of NaClO has a pH of 10.50. Calculate the number of moles of NaClO used to make the solution. Okay, this is a slightly more complicated situation. However, we can easily do this. So the big thing is when we see a solution that is a salt, okay, like this, what we first of all need to do is we need to analyze that salt and figure out what are the reactions that are important here. Okay, so the first ion we have here is Na+. Well, Na+ is the conjugate of NaOH. That's a strong base. So we therefore know that this is not going to affect our solution at all. However, ClO- is the conjugate of HClO, which is a weak acid, so it will. Okay, so that is our reaction. That's the important reaction here. This is the one that is going to end up being our equilibrium. So we're go ahead and we're going to start by using a rice table. Our reaction is ClO- plus H2O goes to HClO plus OH minus. Okay. Again, H2O is a liquid, so we're not going to be worried about its components during the thing. How about some initial things? Well, initially we know that the concentration of the acid and the hydroxide are going to be 0. ClO is what we don't know, so I'm just going to call that Z for right now. Okay. All right, so let's go ahead and look at the change. So for ClO, it's going to be minus X, and plus X for the OH and the HClO. Then for the equilibrium concentrations, we have Z minus X and X and X. And we can go ahead and work that out then with our KSP or KB expression here. But what we do also know is they gave us the pH of the OH minus. Okay, so we're going to go ahead and take the pH, knowing that that is 10.50. Okay, but we're dealing with OH here, so we're going to take and translate that to POH. So POH equals 14 minus pH, which means my POH here is going to equal 3.50. Okay, that then means that my concentration of OH minus equals 10 to the negative 3.50, which equals 3.2 times 10 to the negative 4th molar. Okay, so I'm just going to replace that. 3.2 times 10 to the negative 4th molar. 3.2 times 10 to the negative 4th molar. And then Z minus X would be Z minus 3.2 times 10 to the negative 4th molar. All right, so then where we need to go next is we need to go to KB on this, okay? So KB equals the concentration of HClO plus times the concentration of OH minus all over the concentration of ClO minus, okay? And that's going to equal the KB of value. So you could look that up. However, we don't have that, but we do have the Ka of the conjugate acid, which is HClO, and we know that that is 3.0 times 10 to the negative 8th. Okay, well, we know that Ka times Kb equals 10 to the negative 14th. So if I solve for Kb, that'll give me 3.3 times 10 to the negative 7th, okay, which I can then use down here in my expression. So we're going to go ahead and we're going to fill these in. So HClO is 3.2 times 10 to the negative 4th. OH is 3.2 times 10 to the negative 4th. ClO minus is Z minus 3.2 times 10 to the negative 4th. And that's all going to equal 3.3 times 10 to the negative 7th. All right. So now what you're going to do is you're going to go ahead and you are going to do a whole bunch of algebra to solve for Z. And if we do that, we will find out that Z equals 0.31 molar. Okay, so that's the molarity, but what they're asking us for is the number of moles in 2 liters of this solution. So we know that molarity equals moles per liter. So in this case, 0.31 equals the X number of moles per 2 liters. And so if I go ahead and I do that multiplication, X equals 0.62 moles.